Swayam Prabha. Digital India. Educated India.
So welcome back everyone, and in this module we will be looking at the motion of the precessing frame, right? So what we had was the motion viewed from the precessing frame, frame K, the motion viewed from the precessing frame K. So what we have is that omega here is A cross A dot. That is what we had found. The angular velocity is A cross A dot plus C times N. So this is plus N times A vector A, and this is going to be, so this is A cross L by A, K cross A, and then this is plus L cos alpha by C. So we are just substituting the values. So L cos alpha by C times A vector, right? So these are, so this is from our previous results where we are now looking at the motion with respect to the precessing frame, right? So the precessing frame is the frame which is fixed, right? So not the frame where the axis, the fixed axis is A, but the fixed axis now is K at this point. Okay, so where we have now plugged everything. So now so this is the eventual goal. So the precessing frame is A. The precessing frame is A. So let me draw the diagram here. So diagram is, this is the fixed object, and we have the precessing frame A, and we are observing the motion of this object in this frame, and this frame is also rotating about this axis A, right? So typically that is the motion of a top. So now in this axis A, so in precessing frame, this second motion where it is spinning about this axis A, we will for the time being we will shut down. We will assume that this is not the case. So the only motion is this motion about the axis K. So in the precessing frame, the vector A is at rest. So what we have is that the apparent angular velocity omega prime this time is L cos alpha times A minus C by AC. So L cos alpha A minus C by AC times A, right? So this is what we have. And then what we do is, how did we get? This is this motion. We are talking about this quantity here. What have we done? This angular velocity could be written, I just skipped one more step here. So this was also equal to A cross, this was also equal to L over A K hat plus L cos alpha by C times A minus C by C A, right? So this is the case. So from here I am just looking at the component which is along this vector A, because that is the motion when we that is the apparent angular velocity in the frame A, right? So that is the precessing frame. So the precessing frame, the angular velocity again is a constant. So now we can start to summarize so far what we have looked at. So we have now started to look at two motions. One is about the fixed frame of reference, and the other motion of this top or this object, spinning object, is motion about this moving frame. So the frame itself is moving, but the object is also moving about the moving frame. right? So what we have is, so in the precessing frame, the vector A, is at rest. The vector A is at rest, right? So this is what we have seen. So the summary of our discussion is that the axis which makes the summary is that the axis of symmetry makes a constant angle alpha, with the angular momentum L of k, and it precesses around the axis g comma k with constant angular speed L over k, with constant angular speed L over a. Okay. So and then so this is the L over k, this is this component of the angular velocity, and then we also have a spin. So the spin is also constant. The spin n of the body is L cos alpha by c, which is this component which is along a direction. Okay, so then we can see that this is also equal to, just substituting the cos alpha value, by doing this necessary simplification, not substituting the angle, that this is also equal to L cos alpha times A minus C divided by AC. Okay, so these are just a repetition of what we have seen so far. Okay, so let us look at one example in our discussion. The example says a frisbee is spinning with constant angular speed, right? So it is spinning with constant angular speed omega about its axis of symmetry when its motion is slightly disturbed. So what is the angular speed, the angular frequency? What is the angular frequency of the resulting wobble, right? So the idea is that we have, again, this motion is so there are two sets of motion of this top. One is, of course, the motion around a fixed axis k, and of course the second one is the motion around the moving axis a, right? And we have to find the resulting angular frequency. And so now so the idea is, suppose the new angular momentum of the top is L of k. So suppose the new angular momentum of the frisbee is L of k with the axis of symmetry making an angle alpha. So this is the angle I am talking about. So then with the fixed axis, with this axis g comma k, right? So we have that this is g, and g is the center of mass of the object. Okay, so then what we have is the axis of the frisbee, the axis of the frisbee precesses around this axis with angular momentum L over A. Right, so precesses around G comma K axis with angular speed L over A. Right, so this is the so-called wobble. So this is my wobble here, and then suppose we have the angular momentum around the spin axis. So how about this second axis which is also spinning? So what happens to that? So the angular momentum about the A axis, so it is going to be differing slightly from the disturbed state. So what we have is, so this is also my E3 axis, the spin axis, and it is going to differ slightly from the undisturbed state, right? So it differs slightly different from the undisturbed state, So then the state is C times omega is L naught, and then in this case the precession rate is C omega by A, and this is my angular frequency of the wobble. So how did we come to this expression? Our C omega is our L naught, and our expression for the angular velocity was L over A. So I substituted L equal to L naught. So this is the angular frequency of the wobble. Okay, so then now for a disk, so this is I'm talking about a frisbee. So the frisbee is a disk here. So this is also a disk. So I just want to clarify the listeners, this is a disk. So for a disk, what we have is that C is equal to 2A. This is simply using perpendicular axis theorem. So C is equal to 2A, the moment of inertia about the perpendicular axis. So what we get is our angular frequency omega bar of the wobble is 2 omega. So if we substitute C equal to 2A, we get omega equal to 2 capital omega. Right? So then we would like to proceed further. Right? So I want to see what other motions of the tops are possible. See, the top, when you throw these objects, the spinning top, not only this top rotates in a trajectory which is centered around an axis of a cone, but also the top is going to revolve around its axis of precession, right? So that is the second rotation that we have seen. But not only that, we will see that this rotationary motion is imperfect. The top also does these small oscillations about these rotational axes. These are also known as nutation. Now the listeners can do a little bit of Google search and find out that what are the different set of motions of a spinning top. So the actual motion is very, 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 very complicated, right? So right now we are trying to grasp some of these motions one by one, right? So we have now grasped two motions. One is the rotationally motion about the fixed axis, and the other is the rotational motion about the moving axis or the symmetric axis. Now let us see the second case. So then what we have is a spinning top. So suppose the spinning top has this, this is the top here, and of course this is the center of mass of the top. So this is mgk, and the spinning top has this axis of rotation A, and this perpendicular axis is K, right? And then suppose its vertex is fixed at the origin, and of course, since this vertex of the top is fixed on some surface, the surface is going to exert some reactionary force, let's say X. So let me write down all this setup. So a spinning top. So the vertex of the top is set up at O, and the force exerted is by the reactionary the force exerted by the surface reaction. The reaction is x, and this is from the table. Okay, so we see that if we were to take the moment, about O, right? We see that L naught dot is K naught, right? And in this case, what is my K naught? So we are taking our origin of the axis is at the point where the top is touching the floor. So we expect that this force X is going to disappear when we take the moment. So K naught is going to be, well, just for the sake of writing, is 0 cross X. So 0 means the distance of the normal from the normal force to the origin, and that is 0. And then plus h times a. So what is h? H is the half length of the axis of the rotation of torque of the top. So ha cross with minus mgk, right? And this is also equal to minus mgh a cross with k. Okay, mgh a cross with k. So we have the mass. And this is the mass here. So m is the mass. Okay, so we are left now. So the complete torque is being driven by the weight of the object itself, right? So now what we get is, how about the angular velocity here? The angular velocity is omega is a cross a dot plus lambda times a, right? We see that L naught is a times a cross a dot plus c lambda times a. So what we have is L naught dot is K naught, or well, now we are plugging it into our angular momentum equation, or ddt of a cross a dot plus c times lambda a is so this is equal to the torque here, the torque exerted by the weight. So this is equal to minus mgh a cross k. Okay, so then we can expand this derivative further. So this is also going to be a times a cross a double dot plus c times lambda dot a bar plus lambda a dot, and this is also equal to minus mgh a cross k, right? So this is my, now, so this is the equation that we have derived, and this is the equation for the motion of the top. So this is the motion, the top motion of the top. Okay. Okay. So we have further we know that in this setup we expect that lambda dot is 0 or lambda is a constant. So this is the spin. This is the spin of the top, right? So this is the spin lambda here. So the spin of the top, well, this is the same spin, or this is, well, this is the spin, what we are calling as the spin here, the spin here. Okay. So the spin is about the fixed axis k. Okay, so on top we are assuming that the spin is constant. Okay, so then let us look at a simpler setup. With this all complicated equation of motion, let us try to look at a relatively simpler case. That is, the precession is steady. Okay, so steady means that the object also maintains a constant angle with respect to the vertical axis. right? There could be unsteady motion where the angle with the vertical is also changing or maybe periodically changing. So that is a different case. So what we look at is a case of steady precession. So suppose the axial vector A maintains a constant angle alpha, right? And with the vertical and precesses around the axis O comma K, right? With constant angular speed omega. So what we have is, this time we have that A dot is omega cross A, and this is also equal to, so omega is along the K axis, so this is capital omega K cross A, right? So let me call this as 1. And now suppose we integrate this equation, right? So we integrate to see whether the steady precession occurs. Well, we want to investigate whether the steady precession occurs. So if we want to investigate, right? So we see that A cross A dot, this is also equal to A cross omega K cross A, right? So what we have done is we have taken a cross product of this object with respect to A dot, and we see that this is going to be on the right hand side, this is going to be omega A dot with A times K minus omega A dot with K times A, and this is also, so this is 1, and this is also equal to omega of K minus omega of A dot with K times A. So we can call this as omega cos alpha. So this is A dot K. So K is the vertical axis and A is the rotating axis, and they both make an angle alpha. So this is going to be omega cos alpha times A. So this is my A cross A dot. So now if we were to differentiate this equation, so ddt of A cross A dot, then this is going to be this is omega cross A, so ddt of omega K, so this is going to be 0 minus omega cos alpha A dot, right? So minus omega cos alpha A dot, and this is also going to be minus omega cos alpha A dot is going to be K cross A, right? So that is what we have now. So then so we can finalize this. So my equation, so this is A cross A dot. Now what was my equation of motion? Equation of motion was ddt of A cross A dot, right? So now let us plug everything here in this equation of motion. We see that now my equation of motion reads as follows. So this is going to be my equation of motion. So what equations am I using? I'm using this equation, let's say equation number 2, and I'm also using the equation of motion. Let me call this as equation number A here. So now using A and 2, we see that the equation of motion is A cos alpha omega square minus Cn omega plus mgh, right? So this is equal to times A cross K is equal to 0, right? So this is the case for a steady precession when when we have the top making a constant angle with respect to its moving axis. Okay. So then, well, we can conclude further that A cross K is not 0. So this is not 0, right? Otherwise, if cross product is 0, which means A and K are collinear. That is not the case. A is typically making an angle alpha. So we expect that this quantity here in the bracket is going to be 0, and this is going to be a quadratic equation for omega square. Right? So this is a quadratic equation for omega square. So let me call this, so quadratic equation for omega square, right? So so let me call this as equation, this equation number 3, and we see that well, we could have, you know, one root or double root and so on and so forth, real roots or complex roots. So we can categorize some results. I would like to categorize some results. Some interesting outcome can come from this equation number 3. The outcome is that suppose the discriminant of this quadratic equation is 0, then we of course expect only one solution. How about having the discriminant positive? So suppose we have so if we have a real angular velocity, if and only if we have a positive discriminant of equation number 3. So if we have Cn square is greater than equal to 4am gh cos alpha, right? And then if we have alpha greater than 90 degrees, then cos alpha is always negative, and we expect, let me call this equation number, well, what was my previous, 3. So let me call this equation number 4. So for alpha 90 degrees, 4 always holds, that is trivial, always holds. But what is this case? If we look at the top here, then the top is, you know, making an angle alpha which is greater than 90 degrees. That is not possible, because the top is above the table and it has to make an angle which is less than 90 degrees. So only possibility is that alpha has to be less than equal to 90 degrees, right? We will see later on that alpha equal to 90 degree will not be the case of top, but the case of gyroscope. That is in the next module. So so we wrap up our discussion to see what happens to this equation number 3 when we have the real roots, right? So for alpha strictly less than 90 degrees, the equation 3 is going to give us two roots. So omega will come out to be, let me write down the two roots. This is c times n plus minus square root cn whole square minus 4amgh cos alpha divided by 2a cos alpha, right? And we see that if we try and rewrite this, so this is cn by 2a cos alpha. This is 1 plus minus. Now let me write this in the form of the square root. So 1 plus minus 1 minus 4am gh cos alpha by cn square. So this is to the power half square root, and now we take a using the binomial expansion, we take a so this is roughly equal to, so this is cn by 2a cos alpha, and this is 1 plus minus, so we take a binomial expansion, so this is minus, so 2am and so on. And if we see the positive and the negative roots, we will get two roots. One of them is, we call it as the so-called fast root, which is the larger of the two roots, the fast omega. So this comes out to be cn by 2a cos alpha, cn by 2a, sorry, a cos alpha, right? So 1 plus 1, so that gives a 2, and which cancels with the 2. So that's the fast root. And then we have the slow root, the minus of the 2, which comes out to be mgh by cn, right? So notice that the fast route, it depends on the alpha. So it depends on alpha, right? So, which means that the larger is the value of alpha, the faster it will rotate, right? And we see that the slow route, it depends on, it is independent of alpha. So this is alpha dependent, and this is alpha independent. Now, it turns out, so what exactly what we are seeing? It turns out that in physical reality, the fast route is rarely seen, right? It is, we have to be extremely observant, and we have to perform this experiment of spinning top in a very controlled environment to look at, to eventually arrive at this alpha dependency fast route. The slow route is the one which is mostly visible, the one which is alpha independent. So again, this is a case of steady precession. So thank you so far for listening. And in the next module, I will be looking at some examples, and then we will be looking at some examples of the steady precession, and followed by some examples, some case studies where the motion is in the general 3D plane. So right now we just looked at the 2 axes of rotation. How about when we incorporate all the 3 axes, all the 3 angles involved in the rotation, that is the so-called Euler angles. The motion will be truly 3D. So thank you so far for listening.